in a mass spec that it can, what type of species can the detector see? Neutral, negatively charged, or positively charged species? They have to be positively charged. Okay? Now there are some modes where you can actually detect anions. That's a newer development, which is kind of cool. But the main thing that we look at is a positive charge. And we have to look at what? The M over Z. Mass divided by charge. So if you had something of a mass of 100 over 1, okay, that would show up as 100, M over Z. But what if the charge was 2? What would the number shoot out on your screen? What? I can't hear you guys. You're whispering. 50. Okay? So if you see a value of 50, you can't say, oh, the mass of my molecule is 50. You have to ask yourself, well, what's the charge state? And if it's a +2, then how would you find the actual mass? You would have to multiply it by 2, right? To get to the 100. And so when we are looking at the mass spec, or if we want to take a mass spec of a peptide, there's some issues that we run into. The typical mass spec that we look at, small organic molecules, works great for small molecules, but does not work for proteins. And the one major issue is that proteins cannot go into the gas phase very easily. They're too big. So they're just going to stay in the solution here.
Sorry, just quickly. Z is the charge state.
Yes. So you have this issue, and the way that we would describe it is that a protein in a mass spec won't fly. Meaning when you take your small molecule and it vaporizes into the gas phase, you can push it through the machine really easy, but if the protein's not in the gas phase, it's just going to sit there. Okay? So they've developed these electrospray mass spectrometers, okay, that can now get the protein into the gas phase, but they do it a little bit differently. So with a protein, okay, represented by that little circle there, we're not going to spray it with an electron gun and knock off an electron to make it positively charged. Because even with mass spec with proteins, it has to be positively charged. Small molecules, we take off the electron to get the positive charge. But with proteins, what we do is we add some acid. And what's going to happen when you add acid? You're going to add protons. So if I add 1 proton, what's the charge state going to be on that protein? It's going to be a +1. If I add 2 protons, that's going to be a +2. And so on and so on and so on. So when you take and add some acid, typically the best acid to use is formic acid. I personally have used acetic acid. But when you read the literature, a lot of people say don't use acetic acid because that's going to suppress the signal. The best acid to use is formic acid. So when you add formic acid, you have this massive protein with many, many basic sites that can grab a proton. And so when you shoot that into the mass spec, you're going to get a mass spec that looks like that. And that's of the protein. And so each one of those signals is a different charge state. Now, if you come back here to this slide right here, I'm no analytical chemist and I don't design these instruments, but it's amazing that there's smart people out there that know how to do these types of things. But what it is, it's the electrospray. So you see here you have high voltage right there, and your protein is dissolved in a solution. You inject that onto the instrument, and the proteins are protonated because you have acid in there. And somehow with a high voltage and just a very, very thin, tiny needle, they can spray the solution out and vaporize it. It goes some into the gas phase. So they figured out actually how to do that. And now you see that you have this vacuum here where it can suck your protein into the mass spectrometer, separate it by size, or if you have the GCMS, you can separate it by size. Well, I take that back. No GCMS for protein mass spec. Okay, but then you have the mass spectrometer that can figure out the size based off of the same rules, M over Z. Okay? Any questions or comments up to that point? Okay, so when we take a look at this mass spectrum here, what that little inlet is telling us, that's the mass of our protein. Okay, so that's given to you after you figure out what the mass is. You're only going to be given this. And now it's your job to be like, well, what's the size of my protein? What is its mass? What's also not going to be shown is the charge states. These charge states are not going to be there. All you have are those peaks. You know where they show up because you have the x-axis right here that tells you the M over Z, not the mass. And so we have some troubleshooting to go through here. It's like, okay, I see a number, but based off of, if I see this signal right here, I need to know the charge state in order to know what to multiply it by. All right? Is that, but we see here that it's a plus 30. Okay? Now let's think about this for a second. So I just gave you this example where we had this example right here where we just multiply it by 2. Okay? That makes sense because we just knocked off an electron. Okay? So once we see the M over Z, we just multiply it, the mass that we see, by the charge. And then we get the total mass. But that cannot happen with a protein. Any idea why we can't just look at this signal? Okay, so it's given to us in this particular problem. That peak right there is a plus 30. If we go and extrapolate down and go to the x-axis and find that value is 51579.0666. That's the x value. Why can I not just multiply it by 30 to get the total mass of the protein? Yeah.
Just because different proteins, so like might be, if you multiply that by 30, you're getting essentially different proteins.
Not quite. No, but good thought. Yeah. Denaturing, okay, so in mass spec of a protein, it's not fragmenting. That's another cool feature. With small molecules, you knock off the electron, and that makes it very unstable, and then it fragments into smaller bits. But with protein chemistry, no. The protein stays intact. Nothing falls off. Good thought, good thought. What did I do in this picture right here? Here's my hint for you guys. What did I do here? I added hydrogens. In order to get that protein to be charged, I had to add hydrogens. So that M over Z that you're seeing right here, it's not just a naked protein. It's a protein with 30 hydrogens that have been attached onto it. That's what that M over Z is telling us. So because we know, in this particular example, we know that it's plus 30 charge, how many protons were added to the protein? 30. Right? So what we have to do here is think about it in this way, that we have the mass of the protein that I don't know what it is yet. But I do know, based off of this example, that the charge state is 30. And so that charge state is caused because we added 30 hydrogens. And so that is the mass, the total mass of that protonated protein. We're going to take that total mass and divide it by the charge state, okay, which is 30. And that has to equal the m over z. That's what we have here, the m over z. The total mass divided by the charge. And that value came out to be what is shown right there, which is 1579.0666. So if we want to solve for the actual mass of the protein, the one without all the added hydrogens, do you see the equation there? All what we have to do here? If we multiply both sides by 30, the 30 cancels. Okay? And then we have m plus 30, h equals 1579.0666 times 30. Okay? And then what do you have to do? Minus 30 to both sides. Now I put this little h right there to tell you that, just to remind you, that's because there's a hydrogen there. But then in your mind it'd be like, well, that's just a plus charge. Right? Because what can't, and then so when you have, if we just simplify it down, it's just you take the mass that's shown, 1579.0666 times 30 minus 30. Okay, because we have to get rid of those 3 hydrogens that are there. And so what's the total mass when you do that? 47. If you type that into your calculator, you'll get 47,342 Daltons. And is that what the mass spec in our example shows? The numbers match. So you could do that same calculation for any of the peaks. You could do it for the 30, you could do it for that one, or the 40. As long as you know the charge state and the x value here, okay, you can do that calculation. So that's how you calculate the mass of a protein when you know the charge state. Okay, so that's kind of the easier calculation. You just take the m over z value, times it by the charge, subtract it by the charge. Now, we won't get this complicated in the class, but I just want you guys to be aware of that when we do this, okay, this plus 30 right here, that's the hydrogens. You will see when you zoom in, okay, a little bit more here. There's a little bit more signal there. That's isotopic effects, carbon-13 and whatnot, that affects that. And then it gets more complicated because sometimes it's not 30 protons that have been added on. It's going to be sodium or whatever salt's present. And so what is sodium? It's like 30 mass units? I can't remember. So your protein is now going to be 30 mass units larger than what it should be. But for our purposes, we're just going to think protons, just hydrogens. Okay? Any questions up to this point? Okay. Let's take a look at a situation where you don't know the charge. All you have are peaks. How do you figure out the charge of a protein? Or how do you figure out the mass of a protein? Let's do a very, very simple example. Okay, that's our m over z. And on our y-axis will be the relative abundance. So what if I had a peak here and here? And let's say this guy has a m over z of 751. And the peak on the left is 601. And that's all we've got. And I ask you, what is the mass of this protein? So the way that you do this is you need to know this formula. the first thing that you need to solve for is the charge states. If you know the charge states of those signals, then it's really easy to find the mass. So that's your first thing. What is the charge of those guys? And so the formula is the mass 2 minus A divided by M1 minus M2. Okay, so let's establish what those terms mean. So Z is simply the charge state. Okay, M2, let's type that in there, or write that in there. M2 is the peak with the larger charge state, or the larger M over Z. No, the larger charge state. So how do you figure out which peak has the larger charge state? We don't know the charge, but based on looking at that x-axis, which one would have the larger charge state? The one on the left or the one on the right? The one to the left. And why do we know that? Because those two signals represent both the same protein. So why does the one on the left have a smaller value? Because it's being divided by a larger charge state. Follow? So M2 has to be the peak with the largest charge state. We just don't know what that is yet. But we can tell that this would have to be M2 because it has a smaller number. The smaller M over Z. Okay, and then by default, that would have to be M1. Now, when you do this, and you have a more complicated mass spectrum, okay, with lots of signals right here, you have to choose the two peaks that are right next to each other. So you could do those two or those two. Okay? You cannot compare this peak to that peak. The formula will not work. And then what is A? A in our situation here is just going to be the proton. Okay? The mass of the proton, which equals just 1. That's all we have to remember. A is going to be 1. Okay, and so when you see here, what do we do? What is M2? That would be 601 minus A, which is 1 because it's a proton, divided by M1 is 751 minus 601, and that's going to equal 4. Okay? So that 4 right there, that is the plus 4 charge state. Now, where do we assign that plus 4? That's a big question. Is it M2 or M1? And it is that guy. Okay, it's the one furthest to the right when you're comparing two peaks, when you do this calculation right here. So if that is plus 4, and we compared the two peaks that are right next to each other, by default, what would the charge state of this guy be? It would just be plus 5. It would just be one integer up, plus 5. So when you're looking at two peaks, they have to be one charge state away from one another in order for this to work. Okay? And in all the examples that you'll see from me, each peak that are in succession, they're going to be different charge states. Could it be more complicated? Yes. But we're not going to go down that rabbit hole, okay? So we're just assuming, we're making that assumption. And for most mass spec that you'll see, that's true. Okay? So did we find the mass of the protein? No, we have not. We just found the charge. So then what would we do to find the mass of our protein? Remember, we just go back to the first formula. If we have a plus 4 charge, then that would have to mean that we have 4 hydrogens. Because that's how we get proteins to be in the charged state. And what is the charge? we said plus 4. And that would have to equal what? 751. So now just solve for m, which would simply be 751 times 4 minus 4, and that's going to equal 3,000 daltons. And look, what if we did the 601? 601, what would we have to do to find the mass for the 601 peak? We would have to times that by 5 minus 5. And that should equal the same answer. Because it's the same protein, just a different charge state. How are you feeling about that? Okay. Let's look at a different way that you could work on and solve for the mass. There's this formula. You could just calculate straight from the, you could just, instead of finding the charge state and then figuring out the size, you can just go right from the m over z's directly to the mass. And with this formula, P sub 2, peak 2 minus 1, multiplied by peak 1 minus 1, all divided by peak 2 minus peak 1. So peak 2, when we come back up here to our simple example, what is peak 2 going to be? It's going to be the one with the largest m over z. So that's going to be peak 2, and that's going to be peak 1. So when we come back over here, and we just type those numbers in, 751 minus 1, minus 1, nope, not minus 1. We would go what? 601 minus 1 and 751 minus 601. Type that all in your calculator and that will also come up to 3,000 daltons. So there's two formulas. Now on your equation sheet that you should all see, I put it on the Canvas page. It's not 100% complete yet because it's a work in progress, but make sure you're looking at that. So these formulas that we're going over will be on there, but I'm not going to explain in that equation sheet what does peak 2 mean or m over m sub 2 mean. You have to understand the formulas on your own, okay? And know how to use them. Any questions up to this point? Easy peasy? Okay, so that was for proteins. Let's start and look at peptides. The mass spec of a peptide is going to look a whole lot different than a protein. Okay, so there's that formula I just talked about, but here is the mass spec of a peptide. Okay? And you can see the m over z values above the individual peaks there. And so with a peptide, because it's smaller than a protein, we get better resolution. You can see that there's like 5 or 6 distinct peaks, nice and resolved from one another. If you come and actually zoom in on a protein mass spec, you see how it's just mushed together? There's a lot going on there, but we do have one prominent little peak that's the one that we identify. But with peptides, it's just nice and resolved. Okay. So for a peptide, you can figure out the charge state just by looking at the intervals of each of these peaks. So we would just compare the number here and there, And by comparing those two numbers, we can figure out the charge state right away, just instant. Well, not instantly, but relatively fast. I want to show you how to do that, what I'm doing here. What you're going to do is actually zoom in and look at the difference between the decimals. What increment did it increase by? From 0.65 to 0.93 is roughly 0.33. Roughly. Okay? And so that difference in that decimal place of 0.33, why is that so important to me? Or if you come, let's say, look at this one. What's the difference between this decimal and that decimal right there? Like 0.25? So the difference between those is 0.25, and this one right here is 0.33. Why is that so important? It's because if we look at this, what's 1 over 1? 1. What's 1 over 2? 0.5. What's 1 over 3? 0.333. You see what I'm doing here? So if we have something that has a difference of 0.33, what is its charge state? It's a +3 peptide. Or that signal corresponds to +3. So then if I know that, now I know the charge state, so all I have to do is take this value right here, 1328.696591 times 3 minus 3. Okay? So when you look at this peptide right here, you have to do this calculation with the signal that's the farthest to the left. Okay? That one. That's the one that you have to use. Because what are all these signals right here? Isotopic effects. Or isotopes. Okay? So we're looking at the one that's on the far left. Your hand was up, but did I answer your question? Okay.
I was going to ask, because I noticed these slides, these aren't on the slides, and then I didn't see them in the order. These will be uploaded once we have the...
Yep. You'll have them. So then, class, you guys tell me, when you take a look at this, this is probably really, well, let's see, yeah. What's the size of the protein, or the peptide for this mass spec? I don't know the answer to that one. Let's see here. Okay, 1098.3315. What's the charge state on that one? 4. So times 4 minus 4. I get an answer of 4,389.3260. And with mass spec, it's so sensitive that it does go out 4 decimal places. So you can't just truncate it wherever you want. The mass spec is accurate up to the 3, and then you see the significant digits there. Yeah. Is it 5? Yeah. So yeah, when we look at the actual numbers there, when we do the difference, what is it? When we go 0.55 minus 0.5593 minus. Yeah, when you take the difference of these two numbers here, you get 0.2278. That's the charge state. And yeah, you could argue, is that 0.20 0.25. That particular example was not crystal clear, but you as the researcher, you made your protein or your peptide, so you know what you're going to expect. And so in this particular experiment, you made your peptide, you know if you made it correctly what the masses should be, and that's what you're looking for. So in this experiment, I'm not putting on this unknown peptide, I have no idea what it is, to try to figure out the mass. Yeah.
I was gonna ask, like, why don't you just do 1 divided by that? That'd be
1 divided by that.
just take the person.
1 divided by what number?
The 0.22 centimeter. Saying just take the inverse.
So it's, I don't really understand your question other than when you're looking at the difference in the decimal places, that tells you the charge state.
Yeah, but like if you have 0.25, you could just do 1 divided by that, and you get 4, which is your charge rate. Why don't you just do 1 divided by that? Divided by 0.22.
And what does that equal? 4.8?
3.8.
Okay. That's math. Sounds like it's mathing. But I'm just trying to show you that when you just look at it, you just, oh, that's what I did in my research. I just looked at those decimal places. I'm like, oh, there's the difference. So that's the +4 or the +5. And that's what, because I had a spreadsheet that I would type in my peptide sequence that I made, and then the Excel sheet would say, these are the expected M over Z's. And then I would just go to the mass spec, like, there it is, there it is. Or I'd be like, oh shoot, why is my numbers not matching up? And then